Hello students, Physics 15, how's it going? Today we're talking about falling objects and projectile motion, chapter 3, right? I'll do a demonstration. I'll let go of this marker and it magically goes to this hand, right? Well, we all know what's happening. Gravity. There's a force of gravity. This is actually, it's being pulled towards the center of the Earth. You know, Earth is a ball, a massive ball, and we're all on its surface. Well, we're there, gravity is holding us to the surface, right? Satellites orbit, the moon orbits, it's all held by Earth's gravity. You know, there's asteroids that fly by, right? Some of them crash into Earth, or meteors, gravity, right? And the direction they're pulled is towards the center of the Earth. And it's an acceleration. And the good news is we learned all the formulas that we needed in the previous chapter. So that's good news. So let's get into this. Okay. Okay, chapter 3, falling objects and projectile motion. Let me center this a little bit better. Okay, that should be good. Gravity influences motion in a particular way. Yes, it does, very particular. We're going to be concentrating on the surface of Earth. Because we live here. You know, if you go to different planets, if you go to the moon, the force of gravity is different, right? We've all seen movies, videos of the astronauts on the moon, right, bouncing around, because the moon is small, so the gravity is very much weaker there. Okay, how does a dropped object behave? Well, okay, is it accelerated or is the speed constant, right? So we know about acceleration, right? That's like stepping on the gas pedal. So when an object is falling, is it accelerating towards the ground, or is it just a velocity towards the ground, right? It's an acceleration. It's definitely an acceleration. As it falls, it gets faster and faster and faster. It's as though you know, gravity was a car and it's pointed towards the ground and you're stepping on the gas. You're going faster, faster, faster. So Earth exerts a gravitational force on objects that is attractive. So Earth attracts objects towards the Earth. The direction is towards the center of the Earth. Okay, so well, we measure it. So Galileo, right? Galileo lived centuries ago. He did experiments where he measured it. Now it's difficult to measure it directly because things fall very quickly. But he did it by rolling objects down an inclined plane, and he accounted for the angles. And was able to establish that the gravitational acceleration is uniform, right? We talked about uniform acceleration. That's a nice steady acceleration. Well, why do we make a big deal about it? Well, because we see that in nature all the time. When things fall, it's a very uniform acceleration. You know, it doesn't go a little bit quicker and then slow down. No, it just keeps getting faster, 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 nice and even. So uniform acceleration is common, happens all the time. Everything that is being attracted to the ground, we know, and everything that's falling, it's a uniform acceleration due to gravity. All right. Oops. Okay, so this is a good illustration. It just shows that if you were to release a marble, that and then you know, look at it in equal intervals of time, the distance gets gets larger, larger, larger as it goes. So it is indeed accelerating. It's not just going down at a steady rate. It's going faster, faster, faster. And that's all that's showing. Okay. So, and they're just quantifying that. So, and this table shows, so what's good about this table is that everything, everything on Earth does what this table is doing, right? Everything falls at the same rate. Now we're disregarding air resistance, right? We all know air resistance is quite strong. If you're driving in a car at 60 miles an hour, well, roll the window down and stick your hand out, right? There's a lot, you can feel air resistance. So air resistance is it's strong. So we're going to be ignoring air resistance for the time being, just to simplify our equations. But you can see, so here, what's happening is that the time is increasing in 0.05 second intervals, right? So it's going to 10, 15, 20, 0.25, right? And you can see that the distance is getting larger, larger, larger. You can see the velocity is increasing. Remember, acceleration is the change in velocity. So it goes from 24 to 72, right? So it's getting larger, larger, larger really quick. So, okay. But we understand acceleration from the previous chapter. Now this is just a velocity versus time graph for objects that are falling on planet Earth, and it shows also that the velocity, as you increase time, as you keep monitoring the object that's falling, the velocity increases. Well, that's what acceleration is, right? If you're just driving at 60 miles an hour, the velocity is always the same. But if the velocity keeps getting bigger, 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 that's an acceleration. Yeah, and the slope of the line is constant, right? We talked about that last class. Slope is the rise over the run. Okay, you're changing a vertical versus your change in a horizontal. All right, and the acceleration near the surface on planet Earth is 9.8 meters per second squared for everything. Everything. Footballs that fall, if you throw a baseball and it falls to the ground, when I drop this pen, if we were to measure this, it's 9.8 meters per second squared. That's good news. If it was changing all the time, oh, it'd be tough, but no. So we're always going to have, when we're studying gravity near the surface of planet Earth, it's always 9.8 meters per second squared. Good news. Now here they're just showing an example. They're saying this diagram shows like a ball moving at 10-second intervals, and it's not increasing, it's the same. So this ball is just moving at a steady velocity. It's not changing, so it's not being accelerated. Okay, and we've had enough of that. Okay, so now, right, some people might say, well, if you dropped a feather and a heavy object, if you did this, you know, they've done this on the moon. You can go back and look. If you do this, you know, NASA, where I used to work in engineering, we have these big chambers where you can suck out all the air. If you did do this experiment without air resistance, and you dropped a feather and some heavier object, they are going to land at the same time. If you have a really heavy object, like weights, right, that weightlifters would use, and then you have a lighter object like this pen, and you drop them, they're going to hit at the same time, right? So that's the good news. Everything is accelerated at the same rate. The feather here, right, when there's air, in the room, the air is going to affect it, and of course the feather is going to take longer, right? Just like if you're driving 60 miles an hour. That's why trucks have worse gas mileage than cars, because a truck is higher and it's pushing more air. There's more air resistance, right? So but if you have like a race car that's low to the ground and very aerodynamic. Aerodynamic means is that they purposely engineered it so that the air so that it kind of, you know, just goes through the air, right? That they have like a wedge shape and stuff like that. Yeah. Okay, that all makes sense. We can understand. Okay, so I talked about that. And yeah. Okay, yeah, this book likes to approximate 9.8 meters per second squared as 10 meters per second squared. I don't like that, but I'll keep my opinion to myself, right? So I'm not going to change the homework problems just because the book does it, but just keep that in mind. The real value is very much closer to 9.8 meters per second squared. But when the book does 10, you know, we'll do that, right? I think on my test I'm always going to use 9.8. We'll see. Yeah, so here, and it is easier to use 10, right? Because we have a base 10 number system. So each second, when an object is falling, its velocity increases by an additional 10 meters per second squared, right? That's acceleration. So that's why they use, they're using 10. I mean, it's easier for us to just deal with that in our brain. Yeah, so starting from rest, the velocity of this object that they drop has increased to 10 meters per second. That's a velocity after the first second. To 20 meters per second after 2 seconds, to 30 meters per second after 3 seconds, etc. Right? So that's just illustrating. And then here, you know, they've done a convergence. 10 meters per second is 22 miles per hour. 30 meters per second is 70 miles an hour. Quite quick. Objects fall quickly. Okay. Yeah, distance. Okay, and right, we've done these calculations. You've done this in the homework. Distance is 1/2 AT squared. I'm not going over that again. Go back to chapter 2, right? So that's good news. You already know how to deal with acceleration, formulas and equations that deal with distance and velocity, right? You know how to do that already. Okay. And we'll keep going. Yes, now if you throw a ball downward, right? So I've been dropping my pen, but what if I throw it down? Well, it goes faster. So what you do is you add the initial velocity when it leaves my hand, right? So you add that, and then gravity takes over. But yeah, it's going to go quicker because you've given it, when it leaves my hand, it has right at that, just at that minute second when it leaves my hand, it has an initial velocity, and then gravity just takes over like normal. So it will reach the ground more rapidly. If you throw something down, right? You throw something down, it's going to hit harder. If I took this pen and threw it at the floor, it's going to hit the floor harder than if I just let it go and hit the floor, right? So we all know that. But in physics class, you can calculate very precisely, right? So yeah, so the velocity will be your initial velocity, v0, plus the acceleration due to gravity times the time interval. And then distance, we've seen this, v0t plus 1/2 AT squared. You're already pros at that, right? You've learned so much already, right? You've only been doing this a week. Look how much you know. Okay, now if you throw a ball upwards, this is a good mental exercise to consider this. So if you throw a ball, what if I throw the pen upward? Oh, let me get this in the camera. What if I throw it upwards first, right? So I don't want to do it too much, but if it goes up and then gravity, right? So it goes up. So it goes. Where is this? It goes up. Right? It's so when I throw it initially, it's the second it leaves my hand, gravity is slowing it down. So it leaves quicker, right? So it goes. So when it leaves my hand, it has initial velocity, but it instantly starts slowing down right away till eventually it stops just for a minutia of time, and then normal gravity, then it just starts falling like normal, right? But as soon as it leaves my hand, it's slowing down right away. Okay? And this just shows, right? So you throw a ball, as soon as it leaves your hand, it has a velocity, but it starts slowing down right away, right? They throw a football, you throw any object up, it leaves, it'll go up, it's slowing, stops just for a minutia of time, and then it then just normal gravity and it's falling down. Okay? And that's what I said. All right, you can do that. Yeah, and then this is just showing when you first throw the ball up, it has an initial velocity, and gravity is slowing it down. Here, the velocity right at the top, just for a moment, is at 0, and then the velocity is increasing in this direction. And here they're saying, right, that they're calling this plus velocity and that's minus velocity, right? So that you can do the math, it's direction, right? So it starts with a velocity here of 20 meters per second. When it leaves this individual's hand, it's getting slower. Right here, it's at 0, and then it starts increasing in this direction. And that's what that is, okay? Okay. I could just read those things, but I'm ad-libbing. Okay, projectile motion. Let's do another, we'll do that in a separate video. What do you say?